Good evening to you, viewers and subscribers. Welcome back to the channel and welcome back to another video. In today's video, I'm going to teach you how to design a one-way reinforced concrete floor slab. So this presentation involves a lot of calculation, as I've mentioned to you in previous videos and in some of my monologues, that structural engineering is just merely physics and mathematics, and it involves a lot of calculation. So for those of you who find the video interested, you have to follow what I'm saying and you have to look at the formulas to have an understanding of as to how the calculation is done. So watch the video until the end, like, share, and subscribe. All right? Thank you. So this is it, folks. So the design of a one-way slab. So I'm going to start out by showing you the design parameters. So we are using a live load of 40 pounds per square feet or 2 kilonewtons per meter square. Floor finishes equal 1 kilonewtons per meter square, or FC prime, which is the compressive stress of concrete, is 3,000 pounds per square inch or 20 newtons per millimeter square, and our yield stress of steel is 60,000 pounds per square inch or 414 newtons per millimeter square. All right. So if we look at the slab, so this slab is a simply supported slab. The dimension of the slab is 12 feet by 25 feet or 3,600 millimeters by 7,500 millimeters. All right. And this is how it looks in our section. So we're going to design for this bottom bar here for flexure or bending, and we're going to design this top bar here, these two top bar at the left and right at the upper column of the slab. We're going to design those rebars for cracking. All right. So when the uniform distributed load is spread over the slab, this is how it's going to behave. This arc line you see here, a sag, that is how the beam, that is how the slab tends to behave when it's undergoing a uniform distributed load. So we are going to design this slab. So please to look at it very carefully. So step one is to determine if the slab is a one-way or a two-way slab. All right. And how we determine if a slab is one-way or two-way is the ratio of the long side divided by the short side greater than 2. Okay, if it is less than 2, it is a two-way slab. But as long as it is greater than 2, it is a one-way slab. So we're going to test that. Okay, so we have 7,500, which is the long side, this side here, and we have 3,600, which is a short side here, and when we divide that, we are getting a result of 2.08, which is greater than 2, so that means we are dealing with a one-way slab. Now, to explain a little bit about one-way slab, a one-way slab, the bending of the slab, this sag here is going to be in the short direction. Okay, in the short direction, which is the 3,600 millimeter section or length. It's going to bend about that length, not at the 25 feet or 7,500 feet direction. It's going to bend about the 3,600. So bending is going to take place here, right, in the short direction. So when we're designing, as I've mentioned to you numerous times, we do not design for the entire dimension of the slab. We only design for a 1 meter strip or a 1 foot strip. But for this calculation, I'm going to do it in metric, so we're going to use meters instead of feet and inches. So we're going to take a 1 meter strip of the slab and we're going to design the slab. All right, and design the reinforcement. So now that we have established that we are dealing with a one-way slab because the ratio of the long side and the short side is greater than 2, we can start to go into the design. So step two, we're going to estimate the thickness of the slab. So the thickness of the slab, table 9.5a, the ACI for a simple supported slab is going to equal to L over 20. So let me show you where I get that from. All right. So if you look at table 9.5 here in the ACI code, it says minimum thickness of a non-pre-stressed beam or one-way slab unless deflection are calculated. This is the table that we are going to use. So for a simple supported slab, right, one-way slab, we're going to use L over 20. Right? If it was continuous, we will use L over 24. And if both ends are continuous, it's going to be L over 28. And if it's a cantilever, we're going to use L over 10. But for this instance, we are dealing with a simple supported slab. So we're going to use L over 20. All right? Let's get back to the calculation. Right? So we use L over 20. So our minimum height is going to be L over 20. And L over 20 is going to be equal to H, which is 3,600 millimeter, the short direction, divided by 20. So we get a thickness of 180 millimeter. So the thickness of this slab, based on the code, the length divided by 20 is going to be 180 millimeters. All right. So therefore, we're going to try a 180 millimeter thick slab, assuming a 25 millimeter cover and number 4 bars, which is a half inch or 30 millimeter or 12 millimeter diameter bars. All right. So we're going to calculate now our effective depth. Our effective depth is going to be the 180 millimeter that we just calculated a while ago minus the cover, which is 25 millimeter, plus the 30 millimeter diameter bar divided by 2. When we work that out now, we are getting 148.5 millimeter, and we can round that up to 149 millimeter. All right, so this is what I'm talking about now. So this is the depth of the slab here, and remember we take a 1 meter strip. So 1 meter is equivalent to 1,000 millimeter. So from the top here to the bottom of the slab is 180 meters, and we are dealing with a diameter bar of 30 millimeters and a 25 millimeter, which is 1 inch cover for our rebar. All right, so that works out to be 149 millimeter when we round it up from 148.5. All right, so step 3, we're going to compute the trial factor dead load of the slab. We're going to work out the dead load of the slab, right? So the dead load of the slab is going to be 180 millimeter divided by 1,000, and the reason we divide this by 1,000 is because we want to bring this 180 millimeters to meters times 24 kilonewtons per meter cube. And the reason why we multiply by 24 kilonewtons per meter cube, remember I've said to you before that the unit weight for reinforced concrete is 150 pounds per cubic feet, or 24 kilonewtons per meter cube. So since we want the weight, we times the depth by 24 kilonewtons per meter cube. And when we do that, so we bring that 180 millimeters to meters, which is 0.18 meters times 24 kilonewtons per meter cube, and we get a load of 4.32 kilonewtons per meter square. So the total dead load now is 4.32 kilonewtons per meter cube plus 1 kilonewtons per meter square. 4.32 kilonewtons per meter square plus 1 kilonewtons per meter square, and this 1 kilonewtons per meter square is for our floor finish. So we're going to put tiles on the finished floor. And tiles, we're going to put it on thin set. And you know, tiles, some of them, if especially the porcelain tiles, they are very heavy, so we have to factor that as well. All right, so we ended up with a total dead load of 5.32 kilonewtons per meter square. Our live load is taken as 2 kilonewtons per meter square. And remember, I've said to you earlier that for a residential building, we use 40 pounds per square feet, or 2 kilonewtons per meter square for our live load. Alright, so we're going to factor our live load now. So by factoring the live load, we use 1.4 dead plus 1.6 live according to Appendix C dash C.92 of the ACI. And I'm going to show you where that comes from. Alright, so this is where we get the factor load from. U equal 1.4 dead plus 1.7 live. So this is the required strength. So the required strength U to resist dead load and live load L, the dead load D and the live load L shall not be less than U equal 1.4 D plus 1.7 L. Okay, so that's where that comes from. All right, so after we factor our load now, so it's going to be 1.4 times 5.32 kilonewtons per meter square plus 1.7 times 2 kilonewtons per meter square. That works out to be 10.848 kilonewtons per meter square, and we'll round that up to 10.85 kilonewtons per meter square. So our factored dead load and live load comes up to 10.85 kilonewtons per meter square. All right, so step 4, we're going to check the required thickness of the slab for moments. Okay, so that formula is BD square over 10 to the 6 equal to moment, right, over 5 kN, right, and that is in kilonewtons per meter for our moments. All right, and let me explain this formula to you a little bit more. So we have B, which is the breadth times the depth of the slab square over 10 to the 6. And the reason we have 10 to the 6 is that we are working in kilonewtons per meter. So if we want to carry it to newtons per millimeter, so when we bring kilonewtons to newtons, it's 1,000, all right, and that's 10 to the 3. And we're going to bring it from meter to millimeter, that's 10 to the 3. So 10 to the 3 plus 10 to the 3, 10 to the 6. And that's how we get 10 to the 6 here. Alright, so we're going to work out 5 kN. So 5 kN is going to equal to this formula here. Phi, the compressive stress of concrete, W minus 1 minus 0.9 W, close bracket, right? And where W is equal to rho, the yield stress of steel divided by the compressive strength of concrete, right? And we're going to take rho as lesser or equal to 0.01, and for FC prime, which is our unit stress of concrete, is going to be 20 newtons per millimeter square, and our yield stress of steel is going to be 414 newtons per millimeter square. So when we plug that into the formula now, W, which is 0.01 times 414 divided by 20, the result is 0.207. All right, so 5 kN now, we can go back here now, plug these values in this formula here and work out for 5 kN. So 5 kN, so in slab and beams, slab and beams is basically the same, the design procedure. In terms of design, we use phi as 0.9. So for flexure, so it's going to be 0.9 open bracket 20 newtons per millimeter square times W, which we just calculated here, and it is 0.207 open bracket again 1 minus 0.59 times W, which is 0.27. When we work out all of these in the formula, the result is 3.24, right? So remember, we are checking the thickness of the slab for moment, so we are using this formula. So we just work out here phi kn. So we're going to work out mu now, which is our moment. So our moment is going to be WL squared over 8. For a uniform distributed load, the formula is WL squared over 8. And I've shown you in previous videos where I've gotten that formula from. So it's going to be WU, which is 10.85, which we calculated here. WU 10.85. And it is 10.85 kilonewtons per meter square times the length, which is 3.6 meter square. We bring millimeter back to meter, so it's 3.6 meter square. Divide by 8, and we are getting a moment of 17.58 kilonewton meter. All right. So we're going to work out phi kn now. So we're going to solve this formula to work out BD square, because we want to find out if the depth, if the thickness of the slab is good enough to limit deflection. And one thing I did mention earlier is that when you use the code, right, for the minimum thickness, which is L over 20, once the code satisfies that and your calculation is good, you don't have to do a deflection calculation. I speak to that when I get to the end of the design calculation. All right. So we work out now. We're going to work out D, right? So when we work out BD square is going to equal to 17.58 kilonewton meter times 10 to the 6th divided by 3.24, and that's going to be 5,425,926 millimeter to the cube. All right. So we want to find D. Right, so we want to find D. So we're going to find the root of this over 1,000, because we're moving from millimeter now to meter, and we divide this by 1,000 to bring it back to millimeter. So when we work out D, the result is 73.6 millimeter. Right, so the minimum D is 73.6 millimeter to keep rho less than or equal to 0.01. Right, since D, which we calculated earlier, which is 149 millimeter, as computed in step 2, exceeds the minimum, the slab is okay for flexion. Right, so we are getting a depth of 149 millimeter. Remember, we calculated that in step 2, right? And the minimum thickness is 73.6 millimeters. So the slab, in terms of its thickness, is okay for bending. All right. Now, step 5. Check whether the thickness is adequate for shear. Shear reinforcement is required in slab if VU is greater than 5 VC. Now, since it is difficult to place shear reinforcement in a slab, the upper limit of VU will be taken as 5 VC. Now, when it comes to reinforced concrete deck, concrete slab, we usually do not use shear reinforcement. But it doesn't mean that we should not check the slab for shear. Yes, slab and beams are similar, and the design procedure is the same. So in a beam, we always do shear reinforcement, right? But for slabs, because it's so thin, when you do the calculation, it's going to show you that our stirrups, so for shear reinforcement, is not necessary. So let's go to the calculation, right? So we're going to work out shear, which is VU, which is WN double times L over 2, which is W times Ln over 2, which is 10.85 meters square, times 3.6 divided by 2, which is 19.3 kilonewtons. So we're going to work out 5 BC now, and that formula is in section 11.2.1 of the ACI code, which is 2 lambda, the roots of FC prime, compressive strengths of concrete, times the breadth times the depth. Right, and we take lambda equal 1. So when we plug that into the formula now, it is VC equal to 0.85 times 2 times 1 times the root of f3 prime, which is 20, times 1,000, which is the 1 meter width, 1,000 millimeter, 1 meter, times the depth of 149 millimeters, and that works out to be 11.32 kilonewtons. So it's worked out to be 1,132,792 newtons. Now we divide that by 1,000 to bring to kilonewtons, so we are getting 11.32 kilonewtons. So therefore our 5VC is greater than VU, so it is 11.32 kilonewtons greater than 19.53 kilonewton. Therefore the slab chosen is adequate for shear. Therefore use H equal 180 millimeter and a defective depth, which we calculated earlier, to be 149. So we have seen now where that shear for this slab is not necessary, and 100% of the time when you do shear calculation for your slab, you're not going to get it to equal that you want shear reinforcement. All right, but we still have to check. All right, so we're going to go to the most crucial step now, which is the design of the reinforcement. So to design the reinforcements, the formula for that is that area of steel equal to the moment, the ultimate moment, over phi times the yield stress of steel times JD. So we're going to assume JD to equal 0.925 times the depth. So we plug that into the formula now. Our moment, ultimate moment, is going to equal to 17.58 kilonewton meter times 10 to the 6. And I've already explained to you previously how I get it to be 10 to the 6. Over phi, which is 0.9 times 414 newton millimeter square times 0.925 times 149 millimeter, and that works out to be 17.58 kilonewtons meter times 10 to the 6 divided by 51353.59, and the result is 342.33 millimeter square per meter. All right, so the area of steel we're going to place in every millimeter square of this slab, we're going to use 342.33 millimeter per meter, right? So that's for our flexural reinforcement. So our area of steel required is 342.33 millimeter square for flexural reinforcement. So that's a reinforcement that goes into the bottom of the slab that is going to carry the load. All right, so we set that aside. So if you look now, so we're going to work on AS provided. So if you go to, we are going to go to the rebar chart now, and we're going to choose that area of steel that is closest to 342.33 millimeter square per meter. So let's go to our rebar chart, right? And we are looking for this. We are looking for a number that is closest to 342.77, 342.33 millimeter square per meter. So let's go to the chart. So this is the chart here. So we're going to use this second column. So this is cross-sectional area in millimeter square per meter, which we have just worked out. We have our bar diameter. So these are our bar diameter, our 10 millimeter diameter, our 12 millimeter, 16 millimeter, so on and so forth. And this is our area of steel in millimeter square. And for this column is our bar spacing. So we're going to use 12 millimeter bar, right? Half inch steel, or 12 millimeter diameter steel. So we're going to look for 342.33, and the closest thing we have seen for a 12 millimeter bar is 377. So we are providing 377 millimeter square per meter, even though the calculation have shown us that we get 342.33 millimeter square per meter. So if we're going to use this 377 here, right, we're going to space the bar at 300 millimeter on centers, or 1 foot on centers. All right, so you see how important that is. So we work out the bottom reinforcement. So our area of steel provided using 12mm bar half-inch steel is 377mm square per meter, spacing at 300mm on center or 1 foot on center. Alright, so we're going to work out our distribution bar now. Right, the bar that is going to distribute the load, or in the United States it is termed temperature and shrinkage. Alright, so for our area of steel for distribution bar, we're going to use the minimum reinforcement, right? And for the minimum reinforcement, it's going to be ACI 712. So to use the minimum reinforcement, it's going to be area of steel equals 0.018 breadth times height. So I'm going to show you where I get that this formula from. The area of steel, the minimum area of steel equals 0.018 BH. Alright? So let me show you where I get that 0.018 from. So we are talking about temperature and shrinkage. Shrinkage and temperature reinforcement shall be taken in accordance with 7.12.2 or 7.12.3. Alright, so this is it, folks. So this is where I get the 0.1008 from for our minimum reinforcement. Alright, so it's going to be, the area of steel is going to be 0.018 BH. Right, so it's going to be 0.018 times 1,000, which is the breadth, times 149, which is the height, which works out to be 268.2 millimeters square per meter. Right, so we're going to look at the rebar chart again for the closest number to 268.2 millimeters square per meter. All right, so we go again looking for 268. So when we look at 268, we have 260 here, but this is less than 268 and we can't go lower than the minimum. So we're going to go to the next number, which is 284 millimeters square per meter using number 10 bars or 3/8. Alright, so if we're going to use 3/8 bar, 10 millimeter diameter bar, we're going to use a area of steel of 284 millimeters square, and we're going to space it right at 275 millimeter, which is 11 inches. All right, so our area of steel works out to be, so we use number 10 bars, reinforced bars, on an area of steel of 284 millimeter square per meter as our area of steel provided, and we're going to space them at 275 millimeter or 11 inches on center. So that is for our distribution bar or our temperature and shrinkage bar. Alright, so we're going to talk about our top reinforcement now. Right, so the top reinforcement, and remember I've said we use the top reinforcement in this instance for cracking. So it's not a continuous slab. We are not only designing one slab. If it was a continuous slab, then we have to calculate the moments at the support. But I'm going to do that in a separate video to show you how to design a one-way continuous slab. Right, somewhat different from what we are doing here, but basically the same. Right, so our top reinforcement for cracking, we're going to use the minimum, and the minimum is going to remain the same. It is 268.2 millimeters square using 0.018 BH, and we're going to provide an area of steel of 284 millimeters square per meter using number 10 bars spaced at 275 millimeter on centers or 11 inches on centers. So let me explain to you now what the drawing is going to look like. So this is the slab in plan. So our main bar is going to span the 12 feet or the 3.6 meter direction, the horizontal bar here in the short direction. Never forget that. Never forget that when you're designing a one-way slab, the main reinforcement goes into the short direction, not the long direction. Okay? In our next video again, I'm going to show you how to design a two-way slab when you put the same amount of reinforcement in both directions. But in a one-way slab, the main reinforcement goes into the short direction, because the short direction is where you're going to have bending, your maximum bending, right? So our short direction is the 12 feet, or 3,600 millimeter, 3.6 meter. So we're going to talk about this bar here, and it's going to run from this point here all the way up to this point here, and we're going to space it at so we have 12 millimeter half-inch diameter bar spaced at 300 millimeter, 12 inches on center as our main bar bottom. All right, that's what we just work out. And for this bar here, the longitudinal bar here, which spans the 25 feet direction, or 7,500 millimeter, 7.5 meter. This is going to be our distribution bar, or our temperature and shrinkage bar, and it's going to span from this direction here, right? And we're going to space it at, we're going to use 10 millimeter bar now. So you notice for main reinforcement we use 12 millimeter diameter bar, and for our distribution bar or temperature and shrinkage bar we use 3/8 bar. So in one instance we use half inch, in the other instance we use 3/8. So we're going to space that 3/8 at 275 millimeter, 11 inches on center for our distribution bar. All right, so one bar, the main bar here, is carrying the load, while this vertical bar here is distributing the load, or it is acting as our temperature and shrinkage bar. So for our top bar here, I usually don't show the dimension on the plan, but it's going to be L over 4. So this distance we're going to measure. So if this distance is 12 and it's L over 4, so we're going to divide 12 by 4. So this distance from here to here is 3, right? So this top bar here is going to run from this point here all the way down, and we're going to space it at 275 millimeter on center, 11 inches on center, and we're going to use 10 millimeter or 3/8 diameter bar. Same thing for this one here. You're going to run from this point here. Sorry. You're going to run from this point here. From this point here to this point here. Same thing, 10 millimeter, 3/8 diameter, 275 millimeter on center, or 11 inches on center. All right. So we're going to come down now to our cross section now. So you see, so we're going to imagine that we cut the slab this way horizontally here, and looking back this direction. Or you can look any direction, either up or down, you're going to see the same thing, right? So our bottom bar here, which is our main bar for flexure or for bending, we use 12 millimeter half inch at 300 millimeter on center, or 12 inches on center for our main bar, so half inch. This top bar here, which is a distribution bar, it is going to be our 10 millimeter, 3/8 inches at 275 millimeter, 11 inches on center. And for our top bar here, for cracking on both sides, is going to be L over 4. Remember I said that to you, L over 4. So this distance here is 12, so divide 12 by 4. So the bar here is from here to here is going to be 3 feet, right? And we're going to space both these bars. So they're going to be 10 millimeter, 3/8 inches at 275 millimeter on center, or 11 inches on center, both ways, right? So these bars are running horizontally here, while these bars are running transverse, right? And the same thing on the other side. So this is the section view, right? So I have come to the end of the video. So this is what the section view look like in section or elevation, and this is what the plan view look like. So we have gone through all the calculation here, and it has shown sign that this slab can stand, because we use the code to guide me in this design, so we can say the slab is optimum to carry the weight for a residential building, not a commercial building, a residential building. So a commercial building, the loads is going to be much heavier, right? So you're going to have more reinforcement. All right. So Next week or the following week or early in the year 2025, I'm going to show you how to design a one-way slab with continuous ends, right? So this is only a one-way slab. So this slab is typically a garage, or if you're building a one room or something, you put a reinforcement slab, a deck over it. So this goes to show you what goes on into the slab calculation, right? To show you how we come up, or we as engineer comes up with the amount of reinforcement and the spacing of the reinforcement. So I hope you find the video informative, and remember to like, share and subscribe, and in the event if you have any question, shoot me a comment, ask me anything, because the more you ask me, the more I learn. You might point out something that I've never captured, and I can learn from it. So that is it, and I'm going to catch you in another video. Maximum respect. Thank you.